Well, hello, everybody. Welcome back to your educational journey, back to your video lecture series. Uh, some great stuff today. I mean, some great stuff today. Uh, as as always, and I don't know, it's just love what I'm doing. Love working with you guys, and love this material. If we could, uh, I'm not getting ahead of myself here, but this begins our journey into, I should say, if you were a biology student, this begins our journey into the understanding or the process of understanding how our body uses, constructs, breaks down energy. So it's pretty exciting stuff. I mean, we're going to look at a couple of concepts today, and they're right there, kind of in the middle of your screen: dehydration, synthesis, hydrolysis. That we will be talking about almost the rest of the uh, semester slash school year, depending on what level of education you are. But exciting stuff, man. I love talking about this stuff, and because it lends to such a deep understanding of how our bodies work. And plus, it really gives us a chance to put hands on using the chemical building blocks, which I love to do, and you may have already gotten a small taste of. Uh, but and probably get tired of doing it eventually. But anyway, but let's get the welcomes out of the way because it's a big group today. If we could all just see how many of us there are, that would make it exciting. The college kids would be thinking back to their high school days, and who knows, if you're from Nevada, maybe you even got friends still there. And the high school students, if you could see the college kids and the direction that you're headed, that would be exciting for you as well. But big group because it's all of us. This is another chapter that both groups get to deal with. So let's call the roll here. If you are a Crowder A&P student, welcome to you. If you are a Crowder biology, welcome to you as well. If you are a Nevada High School student, dual credit, welcome to you. And if you are a Nevada High School A&P student, welcome to you. So exciting stuff. The things that we're going to be talking about today are the macromolecules. Uh, this is it's a two-part series, or at least it's in two parts, I should say, that you will be looking at the four major macromolecules: carbohydrates, as you can see there on the screen, lipids, proteins, and nucleic acids, or DNA, RNA, that kind of stuff. So we're going to be taking a journey talking about those things. And geez Louise, I don't know how, but I'm going to try to keep each of the two videos down under an hour. But man, there is so much stuff here to talk about, not just filler stuff. I mean, it's exciting stuff, especially if you're headed into the medical field. I mean, you've really got to know what's going on here to truly understand how the body's working. So, with that, again, welcome. Thank you for opening this up and playing this video and for being a part of it. And as far as notes, especially if you're a high school student, it's part of your grade. Uh, Draw the drawings, write down the words, all that good stuff. If you're a Crowder College student, hey, that's entirely up to you. The more you write down, the more you draw, the better your understanding will be, the better prepared you will be to in class, to when we talk about this stuff and do things to help learn. The better prepared you will be. So That's entirely on you to what you do there. So, quick little drink of water, and let's get started. All right, let me get us a tray here, an ink. What are we thinking about today? Let's see what we got in here. How about a nice little aqua blue there, and we'll select this layer level of pen here. So we're going to start up here in the left hand corner with the building blocks of everything, of all that we talk about today. There are going to be these two words, monomer, polymer, are going to be the foundation of what we talk about. And it's pretty simple, straightforward. A monomer, as you can see, kind of over here, and plus it's labeled right here. It's just an individual subunit or an individual unit, and it can be a compound, it can be a molecule. It isn't going to be just an element. It's going to be some kind of collection of elements that have been used to build a compound or molecule. And then when I take those monomers and put a bunch of them together, either two for disaccharide or a bunch of them for polysaccharides or whatever the collection may be, then they're polymers. So pretty straightforward. Monomers, individual polymers, a collection of them. But two key vocab words to talk about. Oh, and I meant to always say at the beginning of these videos, hey, take advantage of the situation that they are online, you're at home, wherever you may be, work, whatever, who knows. Take advantage of the situation where you can watch these at your leisure. You get bored, take a little break, come back to it. But just be sure that you give it the due diligence as far as time. Hit the pause button, draw your drawings, write your writes, and just take advantage of that scenario. All right. The next topic, concept to think about is we're going to be right here in the middle of the upper part. Dehydration synthesis, hydrolysis. Let me just go a little bit bigger here. All right, these are the ways that polymers are built or broken down, and it all has to do with the idea of water. So we're going to start here, and this concept right here is what we're going to focus on. The beauty of the efficiency of the body and the way things work. All these individual monomers, and we will point this out every time. And when we were together in class, when we're building them, we will highlight this over and over and over again. You are going to get tired of hearing about the OH binding sites. I mean, you are going to get tired of hearing about the OH binding sites, but it's super important that you recognize it, that you see it, and that what I want you to recognize when all this is done is that when we're looking at either a structure diagram or we're building them with the chemical building blocks, that anytime you see an OH little section, you recognize that, hey, that's where another molecule is going to bind to it. Okay, that is the ultimate take-home message. But here's what happens. I got these two monomers. They each got an OH binding site. Okay, that site, we take two of the H's and one of the O. That's where we get this H2O right here. Okay, that they leave, and then that remaining oxygen, and that's showcased right here, is where I should say, the molecules, the two monomers, bond together. So again, It's called dehydration because water leaves, you get dehydrated, theoretical. It's just a name that kind of drives a mental image of what's going on. The water is leaving, so it's called dehydration. The cell's not really dehydrated at that point in time. It's just water's leaving. It could be called evaporation synthesis for just to kind of showcase that. But it's the idea of the two OHs come together, the water molecule leaves, and the remaining O is where they bind. Okay, that's how they are put together. And again, we will showcase that in class over and over. We'll build monomers, we'll put them together, we'll take them apart, we'll put them together, we'll take them apart over and over again. You will get sick and tired of doing that. Trust me. Hydrolysis is how they are broken apart, and it's the exact opposite. Now I've got this, okay, which was the same thing I had up here, my end product. Now we're going to take a water molecule, we're going to bring it in. So you can think of it as we're hydrating, hydrolysis, or you can think of it as the water molecule dissolves the bond. But what happens? The bond is broken. Okay, the two OH sites reconnect, and then we're back to where we started. So dehydration synthesis builds them, hydrolysis breaks them down. And when I say this is important stuff, and we'll be talking about it a bunch, if you are a dual credit student or you are a bio Crowder student, this is chapter 3, chapter 4, chapter 5, chapter 6, chapter 7, chapter 8 will all deal with this concept. So be sure you're giving it the due diligence to draw it out, write it down, all that kind of good stuff. Okay, so those two, the polymer, monomer, dehydration synthesis, hydrolysis, those are kind of the foundation for everything else that we'll be talking about. And like I said, if you're a biology student, almost the rest of your school year or your semester. So with that, let me close out the ink tray here so I can go back down to my 62 and how do I want to do this? Let's just go up as much as we can. Got to work for right now. Get my pen back out. I do like this aqua. I don't think I've ever used that too much. I do like it. All right, carbohydrates. So our first of the 4 macromolecules, carbohydrates. You can't even begin to stress how important carbohydrates are to us. I mean, we hear about them all the time. And some diets say, oh, yeah, cut your carbs, cut your carbs, cut your carbs. But like anything else, hey, man, we need it. So people get unhealthy lifestyles when they cut it too much. But the reason why it's directed at for diet is because it is sugar intensive. All the molecules we're looking at are all sugar molecules. So mindset is got to lose weight, got to cut the sugars down. That's the carbohydrates. But you cut them down too much, and your body doesn't have the energy that it needs to properly get everything done. So it's a fine line between what's good and what's not good as far as cutting carbs. But some examples, and you'll recognize these. You'll recognize these as things that people try to cut out, especially breads, cheeses, high in sugar amounts. But bread, fruits, cheeses, that kind of stuff. And I got you a nice little picture here. We got some good cheese here. And we got some fruit. We got some bread back here. So those kind of things. Now, our next topic that we got to talk about, super important in this ratio right here. Carbohydrates, and you're going to see this a bunch. And again, we'll emphasize this in class over and over and over again. But carbohydrates are built on a 1 to 2 to 1 ratio. All carbohydrates are a collection of carbons. That's where you get the carbo. Okay. And if you know anything about your chemistry, that you know what this hydrates, what it refers to. okay, oxygen and hydrogen. And so we've got H's and we've got O's. So this 1 to 2 to 1 ratio means for every carbon, there's an oxygen, but there are twice as many hydrogens. So for example, if you've got, let me come down here, if you've got a carbon and there's 4 carbons, draw my H here, then draw my O. There will also be 4 oxygens, and spoiler alert, there will be 8 hydrogens, 1 to 2 to 1 ratio. So if there are 5 carbons, there'll be 10 hydrogens and 5 oxygen. If there are 6 carbons, there'll be 12 hydrogens and 6 oxygens. 1 to 2 to 1 ratio. That's how you can determine, that's how you can spot them when you're looking at the chemical structure, chemical makeup, if it's a carbohydrate or not. 1 to 2 to 1 ratio. Okay, so that's carbohydrates in general. What we're now going to begin to talk about is the different types. There are 3 main types. There are monosaccharides, disaccharides, polysaccharides. So I'm going to move this over here and talk about monosaccharides. I can get most of it done in with this stuff right here, but I think I have to go down a little bit once we talk about these 4. Okay, so we are right here, monosaccharides, mono, 1. Okay, so we're talking about just individual sugar molecules. So these would also be monomers. Okay, these would also be monomers. So let me M-O-N-O MERS. Monomers. And here's some examples. Glucose is a monomer or a monosaccharide. Fructose is a monomer or monosaccharide. Galactose. So what that simply means is that there's just one compound or one molecule within those collections. Okay, so some examples, and so we're going to work with this box right here. Okay, and again, and I should have said this ahead of time. Yeah, if it's the pictures and stuff, let me think about that. No, I better not say that. Scratch what I was getting ready to say there, because it might not always be the case. All right, so now in this box, let me get a little bit bigger here. In this box, we'll be able to do a couple of things. Oh, I didn't mean to do that. I got my ink tray up, so I was going to slide over, but anyway, we're all right. We'll be able to emphasize a couple of things. One, the ratio for certain, okay, and just look at different types. Now, the OSE in a science classroom, especially in a biology or a chemical classroom, you see a word that ends in OSE, okay, that's a sugar. Okay, that's a sugar. So aldose, ketose, triose, pentose, hexose, those are all sugars. And a couple of things to point out, there's always this oxygen with the double bond somewhere. It can be up in the upper branch, it can be along the stem, but somewhere there's an oxygen with the double branch. Okay, and these are just different variations of monosaccharides. Sometimes they'll have a 3 carbon backbone. Sometimes they'll have a 5 carbon backbone. They can be a 4 carbon backbone. This is a 6 carbon backbone. But what you also want to emphasize is that it follows the 1 to 2 to 1 ratio. Because, for example, let's go to an easier one to count. This one has 3. So if it's 1 to 2 to 1, there should also be 3 oxygens. And there are 1, 2, 3. So that means there should be 6 hydrogens. 1, 2, 3, 4, 5, 6. So that 1 to 2 to 1 ratio. If we went over here to the big one, we got 6 carbons. We've got 1, 2, 3, 4, 5, 6 oxygens. And of course, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So 1 to 2 to 1 ratio. So that's what we wanted to emphasize that. But these are just different examples of monosaccharides. And let me close this out. Go back down to my 62. Slide this up. And so for our last topic on monosaccharides will be this box right here. Okay. Now you can see, if you're using a microscope or whatever, you could see compounds in this structure, the linear structure. But what we're going to talk about here is that they can also modify themselves into what they call a ring. And you can see one in the process of doing that here. And the way this is structured then, or where it's red, any of these little points here, that's where the carbons are located. And of course, then you got the 1 carbon up there. So unless it's identified like this oxygen right here, the rest of these would be considered or would be recognized as carbons. In other words, if glucose, which you know has 6 carbons, okay, so it would be, let's see if I'm, I probably should have counted these first just to make sure I'm right about that. 1, 2, 3, 4, 5, and 6. Yep. I got nervous there that I was overspeaking myself, but I ended up being right after all. It happens. So that's the conversion between linear and rings. And you may say, why would it do that? Or what would be a reason doing that? It has to do with just cell processes. Maybe it's being copied. Maybe it's part of a nucleic acid that's being read, and everything's got to be opened up and everything. So, but they can convert between linear, which is up here, and rings, which are down here, and they just simply wrap around and connect at the appropriate spots. Okay, so that's monosaccharides. So let me close my ink tray, and I'm going to scoot over here to disaccharides. And when we talk about disaccharides, that gives us a chance to go back to and reemphasize dehydration synthesis, hydrolysis, because when we talk about monosaccharides, we've only got one, so we can't join anything. But disaccharides, let me get my pen back up here. And let me move this where that disaccharide. Oh, I got my ink tray. I can't move it. Where the disaccharide is not underneath that area. There we go. And ink tray back up. So we're talking about disaccharides. So the di, 2. So we're taking 2 monosaccharides or 2 monomers and putting them together. Now I've got these pictures here, but they're not always clear as what goes with what. So I will identify that image right there. I should have said that disaccharides are used for sugar transport. So we got to move some sugars. So just like a train, okay, we're going to put a bunch of cars together, not just taking one train car at a time and moving it somewhere. We're going to build us a nice long train. And so we want to transport some sugars. We'll put them all together and take them all out at once. Or more likely, energy storage. And this is where the carbohydrates are just these huge energy storage. I mean, they can be massive when you get to the polysaccharides, but they're just real good at efficient storing of energy. When we get to the polysaccharides, we'll talk more about that. So, but this is kind of a before and after. So I'm going to draw me a line right here. This is the before side. We're taking 2 monomers, and this is the after side. So what's on the left is the same as what's on the right. It's just they have been joined together. dehydration synthesis. So here we are, and here, and I've never understood why they display this one as they did, because they highlight this this hydrogen, and this bonding site here, but obviously this is the one that's right next to it, that it looks like over here is where the joint is. This OH is still right there. So anyway, I'm not sure why they made that one red. So just ignore that red and pretend this one's red. But this hydrogen, this oxygen, this hydrogen are going to leave H2O, okay? And then what's left, this oxygen here, will be where they connect dehydration synthesis. And then you get the water reference over here. So again, just recognizing, emphasizing, reinforcing the concept of dehydration synthesis. And when it comes time to break them apart, spoiler alert, we're going to bring some water in, dissolve that bond metaphorically, and then once we separate, we've got back to our two OH binding sites. So again, before, after dehydration synthesis as an example. Speaking of examples, some examples of disaccharides: sucrose, maltose, lactose. Those are some examples. So when you hear those words, you're thinking, all right, disaccharides. All right, and we close the tray here, slide this up, bring my pen back up, and let's draw a square around this one. All this again is another joining of the two monosaccharides, glucose, fructose, and we're going to make sucrose to emphasize that it is an example of a disaccharide. So you take glucose, take fructose, put them together, and that forms sucrose. Okay, and again, but we're doing the same thing, dehydration synthesis. This hydrogen, this oxygen, this hydrogen are going to leave H2O, water, and this oxygen that is left is where they are connected together. Dehydration synthesis. When it comes time to separate it, we're going to bring some water in, dissolve the bond, and then the OHs return, and we have our two OH binding sites. Again, emphasizing how molecules are built, how molecules are broken down. And we will, like as I said, we will build and break down with the chemical building blocks in the classroom over and over and over and over again, trying to make sure that you get those two words down and what's happening. So when I say dehydration synthesis, you say, boom, building molecules. When I say hydrolysis, you say breaking them apart. All right, so that's monosaccharides, that's disaccharides. We will look at our final carbohydrate concept. And again, we've already been up there. And so let's, before I get the tray open, let's make this a little bit bigger. Get my pen up here. And again, so now we're polysaccharides. So we are many, okay, or in this case, more than two. If monosaccharide is one, disaccharide is two, then poly must mean, three or more. But usually they're pretty big. Okay, of polysaccharides, there are four major classes, and you certainly want to write this stuff down. The first two are essentially the same. It's just based on where they are, they've got little differences. But the first two, starch and glycogen, these are energy storage. Okay, starch is in plants, as you can see here, and glycogen is in animals. So if I'm a rose bush and I'm storing energy in molecules, I'm making it into starch. Okay, and we hear starch a lot, especially if you're an athlete. um, rice, pasta, potatoes, those kind of food choices to get that energy sources from the plants. But glycogen in animals, so if you're a cow, pig, uh, chicken, turkey, whatever, you'll be storing those as glycogen. Okay, your two other types of polysaccharides, cellulose, which is that the outside portion or outside part of uh, a plant cell, the cell wall, is made of cellulose, which is why, and we don't do a good job with digesting cellulose, which is why we struggle with some plants, fiber, corn, whatever. But cellulose is what the cell wall of a plant cell is made out of. And lastly, chitin. It's the component that makes up those hard surfaces on insects. So, like the shell of a beetle, if you know anything about bees, they've got this little armor plate right in the kind of where our neck would be. They've got that, but it's that hard part of an insect body. And it says there in some fungus cell walls as well. But that's chitin. Pretty hard, it's similar to what your fingernail would be made of, but that's keratin, not quite the same, but similar in structure and that kind of stuff. So that's the four major types: starch and glycogen, energy storage, plants and animals. Cellulose is what the cell wall of a plant is made out of, and chitin is those hard, structured support parts. Of an insect body. So that is our look at carbohydrates. Let me go back down to 62 here because we got to pull ourselves down here. So now we're going to be looking at lipids. Okay, lipids are super, super important. So we are, get up in here. Let's switch it up. I know I like that blue. I really do. But let's get a different color going here. How about a nice little, let's just go darker blue. All right, so now we're here to lipids. And lipids are unbelievably important because you see right here, they are excellent for energy storage, but they are fats. So when it comes to dietary issues, you really got to watch what's going on with fats. But just like the carbohydrates, we need them. Okay, we need them. And there are different kinds. It's not just about the fats. There's other things, as you can see here, oils, waxes, cholesterol, hormones, some vitamins, that kind of stuff. It's not just about the fats. But when it comes to dietary, you just got to watch what's going on, take care of yourself. And there are ways of incorporating lipids in a more healthy fashion than non-healthy. So you just got to be educated about it, know what you're doing, and do what's right. But the first thing we got to talk about is the idea that lipids are non-polar. And you got to think back to that chemistry stuff we just went through, what non-polar means. Okay, non-polar means it's not going to mix with water. Okay, and that's referenced right here. Okay, it isn't going to mix with water. It doesn't dissolve in water. It doesn't saturate, or it isn't, dissolved by water. Just think if fats could be dissolved in water, mentally you would think, okay, that'd make dieting pretty easy. Just drink a bunch of water, they dissolve the fats. But if that were the case, then you would also lose a lot of energy that your body is trying to store because it would dissolve the fat. So, pros and cons, pluses and minuses of that situation. Okay, something else to point out. not polymers. Okay, they don't have polymers. They don't really have monomers either. They're the one that don't fit that monomer polymer chain. Oh, not chain, concept is what I should have said there. Okay, they are excellent in storing energy, as I mentioned, because they have a lot of carbon hydrogen bonds. When you get those CHs bonded together, a lot of energy involved in that. Lots and lots of energy. And I got a cute little otter here. Who doesn't love watching otters play in the water? I mean, whether you've seen them out in the wild, if you've been lucky enough to see that, or you've been like at a Bass Pro or Wonders of Wildlife, or just a zoo, St. Louis, Kansas City, whatever, and seen them, Omaha, Nebraska. If you've been to that good one, that great one, Wichita's got a good one. But anyway, to see those. Who doesn't love seeing otters play in the water? But anyway, it's got a picture of one because of this idea of oils and waxes. Okay, animals like otters, beavers, some birds, they have these glands that they're able to excrete lipids, and they can spread those across their fur or feathers, and kind of gives that waterproof aspect to them. We do the same we can do the same with our vehicles. I mean, when I was a kid, it was super important to wax your vehicles, your cars, trucks, whatever. But back then, things are made of steel. Okay, now it's more plastic. So the waxing of your vehicles anymore. I mean, I don't even know. Well, as an adult, I don't even know when the last time I did that. Because, like I said, it's more plastic now. And I'm trying to even think, is that industry still around? I don't know. I'll have to go to an auto parts store and see, I guess. Check out Walmart next time. But anyway, it's the idea you can Scotch guard furniture, clothing. You can get a waterproof jacket, and it's simply a jacket that's been saturated with lipids of some kind to make it the water just bead off and run away and not soak into or absorb the water. So that's the idea of waxes. So when we talk about fatty acids, and now I'm right here, we got to talk about the different types. Okay, and a lot of health stuff, nutrition aspects of all this. But saturated fats, okay, these are the ones that are from animals. Okay, they are solid at room temperature. So when I was a kid, when I was in high school, I worked at McDonald's, and when when it was time to change out the oil in the fryers for the French fries and stuff, the nuggets, whatever, we would open up these big boxes. I mean, we're talking about maybe 2 feet tall, 2 feet wide, and you would open these boxes, and you'd have to lift out this big block of saturated, basically fats, and put them in the fryer, and they would melt over time. But they were obviously solid at room temperature because they were extremely heavy, and that was animal fat. Now everybody's pretty much gone to vegetable oils of some kind. They are liquid at room temperature. So at home, when you cook vegetable oil or canola oil or olive oil, whatever you might fry something up in or cook with, much more healthy, plant origin. And I got a picture of a nice cow here and a nice bottle of olive oil there, which I love cooking with, but I like to cook. So, but that's the idea. So saturated, no double bonds, from an animal, solid at room temperature, unsaturated from a plant, one or more double bonds, and we'll showcase that here in just a moment. And of course, the trans fats, the real unhealthy ones that people try to get away from, all that stuff. So let me close out the ink tray. Let me slide over here so we can look at saturated fats, unsaturated. Bring my pen back up here. And all right, so we're going to talk about the two types of fat from a chemical structure. Or they're saturated, there's unsaturated. Now, when it talks about these double bonds, it's talking about this right in here. You can see that, and there's one down here as well. You can see that the double bond's right in the middle. Okay, so saturated has no double bond, as it says over here. And again, it's not in there anywhere. And you may say, what about this over here? Well, that's it. I didn't say it has to be between the carbons here in the middle. So, yeah, they all have it at the end. As we talked about, there's always going to be that somewhere. Talked about that earlier. Now, another thing to point out is that the trans fat, which are considered very unhealthy and people are trying to get away from, if the hydrogens off that double bond are on one side, then you're good. If they're separated, then that's where you get to be that trans fat that people try to get away from. So double bond in the middle for unsaturated, and you're looking for the H's, the hydrogens, to be on the same side. Okay, just a couple more topics to talk about. I'm going to slide. No, I don't mean to grab that. Back over here. Yeah, and I think, yeah, this is all the last stuff right here. So let's just go right here. All right, so let's look at how lipids are structured. Now, our word here, and it's right, let me get a pen here, so I don't have to spell it out for you, but it's right here, triglyceride. So this structure that is here and here is called a triglyceride. Tri meaning three, and you can see the three branches here. Now, so we're going to build this. A triglyceride has a glycerol, and that is both here, okay, and here. So a triglyceride, and again, I should point out that this figure here, so all this goes together, and all this goes together. Okay, it's the same thing. Okay, just one's going this way, the other's going this way. So it's the same thing. So we're going to point them out in both aspects. Okay, so but a triglyceride has a glycerol backbone. Okay, and then just branches, in this case 3, of the fatty acids. And in this case, we can see there is no double bond in here, so it is a saturated fatty acid, and we don't see any of these. So these are all saturated fatty acids. All right, so now this glycerol backbone this is kind of the finished product in here. This is one component. This is another component. So let me draw a square right here and show you that this glycerol is right here. It's just now stretched out. So you can see the 3 branches. Like here's this H. Okay, here's the HCOH, HCO, and then of course we've had some dehydration synthesis, so that one of those hydrogens are gone. And then here's this HCOH, HC, and again, dehydration synthesis, so that H is gone. And then the HCOH, HC, again, dehydration synthesis, and then here's that H at the bottom. So it's the same thing, just stretched out. But what we want to point out is that, okay, this OH bonding site, okay, and these OH bonding sites here, dehydration synthesis. Okay, water molecule leaves. The remaining O is where they are connected. So again, we can't stress enough that we got to have an understanding of dehydration synthesis. Each site, each molecule has an OH, okay, and a hydrogen or two hydrogens and oxygen leaves, and then the remaining oxygen is where they're connected at. And then we have built a triglyceride, a glycerol backbone, and then three fatty acids. Same thing over here. We've got our glycerol backbone. We've got our OHs here. We've got our OHs here. So right away, you should be thinking, boom, dehydration synthesis. Okay, water molecule leaves. So this is the before. This is the after. The glycerol backbone, the three fatty acids. We've built the triglyceride. And then here's a reference to the waters that left. In this case, three, because we put three chains on. So again, that's the process in which a triglyceride is built, the lipids, dehydration synthesis. When we want to break this triglyceride apart, hydrolysis, water molecules come back in, dissolve the bond, the OHs return. Okay, we can't say that enough. We can't say it enough. You can't think about it enough. You got to make sure that you have that concept down. All right, our last topic for lipids, which makes it our favorite topic, because it's our last one, is the phospholipid. And the phospholipid is unbelievably important. Okay, we're going to talk about this thing a bunch when we get to chapter 4, the organelles, in chapter 5, the plasma membrane. We're going to be talking about it a bunch. And you really want to make sure you draw it. You really want to make sure you identify the parts. Super, super important that you understand the structure here. Because it's got so much going on that you will make more sense when we get to 4 and 5. But right now, get your foundation in. All right, a phospholipid. As you can see here, this is like a plasma membrane kind of thing right here. Plasma membrane. And these are the individual phospholipids is what is shown over here. So here we go. The breakdown. It's got a phosphate group. Okay, this is the head. These are the tails. And you can see right here, little double bond. So unsaturated, no double bond, saturated. Okay, again, just reinforcing the importance of knowing that stuff. And we can see that these are fatty acids. And here is our glycerol backbone, okay, that we just talked about, just like what's up here. Okay, that's the way lipids are built. Okay, how many branches you have coming off of that can vary, but that's the process of how it's built. So you got a phosphate head attached to a glycerol backbone, which is attached to the fatty acid. The fatty acids. So phospholipid, phosphate head, okay, and because it has that phosphate head and this little symbol right here, okay, that negative sign, okay, makes it a polar aspect here. Polar. So the head of a phospholipid is polar. The tail is nonpolar, the lipid part. So what that means, it can associate, or at least the head associates with water. And that's how it kind of orientates itself. That's how it allows it to get through the membrane, that kind of stuff. So that little negative sign on that oxygen, super important because it makes the head nonpolar, or I shouldn't say nonpolar, makes the head polar, okay, and now it can associate with water. But we'll talk more about that in chapter 5, the plasma membrane. So there we go. Looking at the clock here, 10:55. I think it was a little after 10 when I started, so maybe I kept it under an hour. Yay me, yay you. But it'll have taken you much longer to watch this because you'd stopped and wrote things down, drew your drawings, draw your drawings, and that kind of stuff. So, but yay me doing that part of it. But again, do your due diligence. Write down what you're supposed to write down. Draw what you're supposed to, what you draw, and don't shortcut yourself. I mean, your grade depends on if you're a high school student, so don't shortcut yourself there. But again, thank you for watching this. Thank you for being a part of this. Hopefully you enjoyed it. Hopefully there's some stuff there that you encountered that maybe was new and got some new insight into how your body is constructed, how your body operates, the manners and stuff, and the processes. But do make sure that you've got a good idea of dehydration synthesis, hydrolysis, because there probably won't be a day, especially if you're a bio student somewhere, there will not be a day that we don't say those words in some context, in some structured environment. But again, thank you. And let's see, next time will just be part 2 of this. Proteins, nucleic acids. And so until then, enjoy yourself. And as always, man, I hope you're safe. I hope everything's going well. Let's see, just looking at the long-term calendar, by the time Veda students, not kids, students watch this, man, we could be October-ish. So hopefully we're still going strong with school. Crowder people, you're going to be watching it pretty fast. Third, second, fourth week in there somewhere. So hopefully nothing's happened that fast. But anyway, again, hope you're safe and sound and everything's going well for you, and that you're doing well with everything. But again, thank you, and until next time, we will say goodbye.